Okay. So thank you so much for having me. I changed my title slightly to be what we know and what we don't know about Great Salt Lake dust, because I think it's important to highlight the things that we are still working on and the outstanding questions along the way. So let's flash backwards in time, 40 years, I guess, at this point, back to 1984. Um, Northern Utah had had several years of unprecedented snowpack, and it actually filled Great Salt Lake to capacity. Its historic high actually was reached in 1987, about 3 years after this image. And then you flash forward to 2022. The lake reached a historic low, dropping all the way down to 4,188 and a half feet from its high of 4,211. So for such a shallow lake, it was a massive decrease in volume, has exposed more than 800 square miles of surface area of playa, and that has caused all sorts of issues. I love Pat Bagley, a political cartoonist here in Salt Lake City. Can say a lot with just a little. Clearly, something is out of order with the Great Basin and Great Salt Lake. So why is Great Salt Lake shrinking? Well, there are really three choices on this, or three potential explanations: climate change, drought, and water diversion. And as mentioned, I'm part of the Great Salt Lake Strike Team, which is a group of scientists at the Research One universities and in Utah and the government organizations. And the hydrologists in that group put together their best assessment of the causes of the shrinkage of Great Salt Lake over the last 40 years. And just to cut to the chase, climate change, increasing temperatures, leading to increased evaporation from the lake, is responsible for about 10% of the water loss during that time period. The ongoing mega drought that we're experiencing here in the Western US is responsible for almost a quarter of the water loss. But overwhelmingly, anywhere between two-thirds and three-quarters of the water loss from Great Salt Lake is due to excessive water diversion for other purposes. And what do we use that water for here in Utah? Well, about two-thirds of it is for agriculture. It turns out to be about 10% for municipal, 10% for industrial, kind of 8% for mineral extraction, and about 10% other uses. And that agricultural sector, what is the primary crop that we're using that water for here in Utah? It turns out that it's alfalfa and hay. We, because of our climate, are able to grow very high quality alfalfa and hay that is in high demand and basically gets top dollar. And so a lot of that alfalfa and hay is actually shipped out of Utah, and about a quarter of it is actually shipped out of the country. For more information and all the details on how that was done, I direct you to the Great Salt Lake Strike Team report. We have an annual data and insights summary that's published. We've done this since 2023. This is our third data and insights summary. And it's always timed to be right before the legislative session in Utah. We have the shortest legislative session of any state. It's 45 days. It starts the third week in January and goes through the first week of March. So, what are the consequences of a shrinking Great Salt Lake? Well, from my perspective, the very first thing that I saw associated with this was dust. And I saw dust coming off of Great Salt Lake in significant quantities as far back as 2010. As the lake shrank, eventually it got so low that they had to remove all the boats from Great Salt Lake because they could no longer support the marinas. Eventually, the mineral extraction companies, the canals that they used to get water from the lake were no longer attached to the lake, and they were in danger of losing access to their product. And more importantly, the shrinkage of the lake led to a salinity crisis that threatened ecological collapse. And if we stayed on that trajectory, it was clear that the lake as we know it would have been dead in about 5 years. So that was the where we were at in 2022. We've since had two very good snowpacks, and it hasn't solved our problems, but it's actually reset the clock and given us another 2 or 3 years to actually work on water conservation efforts. So let's talk about dust. So here is a video of a dust event that happened all the way back in November of 2016. This is taken from the University of Utah campus. We're looking out across Salt Lake City. The Great Salt Lake is to the right. There was a cold front, a dry cold front that passed through, and now it's picking up dust and moving it into our community. This particular dust event reduced horizontal visibilities to less than a mile. Interestingly enough, it did not result in a violation of the National Ambient Air Quality Standards for that day, because our dust events that come from that direction typically only last a few hours. And so we had good air quality for most of the day. The 24-hour average was only about 57 micrograms per cubic meter of PM10. If we look at the seasonality of dust events, our dust events are primarily driven by the passage of cold fronts in the spring and the fall. We can have thunderstorm outflow during the summer if we have a monsoon event, and we do have dust devils that can generate small-scale dust. Generally speaking, the playa is too wet during the winter for dust, but I put a question mark on that because we just had a major dust event on January 21st. It's the first documented dust event that we've had from Great Salt Lake in the month of January. I used to be able to say that I've seen dust coming off the lake in every month except for January, and I can no longer say that. But we've had an exceptionally dry winter at the lower elevations, and I took some soil moisture measurements out a few days after that dust event, and there were pockets of soil moisture out there that were less than 4%, even though there were other areas that were, 30% moisture. So here's an example of one of these dust fronts moving into Salt Lake City. Very distinctive. And here's an example of dust coming off of one of the thunderstorm outflows. And yes, I was getting off the lake bed at this time. Safety first, right? For this group, I don't have to belabor the issue about why we care about particulate matter and PM10. Obviously, short-term exposure can lead to lots of different outcomes in terms of reduced lung function, bronchitis, irregular heartbeat, heart attacks. But the long-term exposure to carcinogens in the dust could potentially lead to various types of cancer. And that's one of the things I'm going to talk a little bit about today. So here's kind of an overview of what I'm going to talk about. So I'm going to start off by what we do know about the dust, looking at the dust hotspot locations, the role that soil moisture and surface crust play in emissions from Great Salt Lake. We'll look at dust composition measurements, bioavailability measurements, and the communities that are most likely to be impacted. So let's take a look at the dust hotspot locations. So in order to answer this question, I embarked upon a long journey of about 2.5 years of doing soil sampling on Great Salt Lake. Started this in 2016, finished it up in 2018. Used incremental sampling methodology, set up grid points every 500 meters over all 800 square miles of playa, and visited them on bicycle. And at each one of those locations, took a soil sample, composited those soil samples into larger groups, brought that soil back to the lab, dried it, sieved it, resuspended it, and pulled out the PM10 fraction, and then analyzed the PM10 fraction using a combination of ICP-MS and synchrotron X-ray fluorescence. In all, we were able to quantify 53 different elements. Just give you an idea of the scope of what I did. Here's the GPS track of the bicycle on Great Salt Lake. It was about 2,300 miles, about 145 days in the field. It was a major effort, one that I hope never to do again. You do it once, you do it right, you never do it again. So everybody else asked me, what do the dust hotspots look like on Great Salt Lake? Well, here's an example. We had a very shallow surface crust that was eroded naturally in this case by saltators, sand moving across the top, and you had deflation in this area. Just give you an idea of how thin the crust was in this region, just a few millimeters thick at most, very fragile. And eventually, there are some areas on the lake bed where these dust hotspots have grown in size and merged into what I would refer to as dust hotspot areas. Luckily, that's not super common right now on Great Salt Lake, but the longer the lake bed is exposed, the more likely we are to end up with these types of dust hotspot areas. So, in order to define a dust hotspot in this context, I basically looked at the superposition of areas on the lake bed that had no vegetation on places that had visible fines that if you disturbed it, you could generate dust, and had naturally either no crust or an erodible shallow crust. And you put all that together, and it turns out that only about 9% of the lake bed in 2018 matched that criteria, which is actually a good thing. It turns out that more than three-quarters of the lake is actually covered by an intact shallow crust, which does a very good job of limiting dust production. So where are these dust hotspots located? It's a little hard to see maybe, but we have basically dust hotspots in all four quadrants of the lake. In the southeastern quadrant, the bottom right, we have what's called Farmington Bay, which is closest to Salt Lake City and most of the residents along the Wasatch Front. There's a blow up of that in the bottom right. And then the upper right, we have Bear River Bay, which is close to the cities of Ogden and Brigham City and Logan and Tremont and up that direction. And then we also, in the extreme northwestern quadrant, we have dust sources, dust hotspots, and also in the southwestern quadrant near the EPA Superfund site, which is known as US Magnesium. So there are dust hotspots, these four, primary areas in each quadrant of the lake. So luckily, through a combination of atmospheric LiDAR and bathymetry measurements, we've been able to merge those dust hotspot locations with a digital elevation model. So we can look at the probability distribution function for where these dust hotspots are located with lake elevation. So on the y-axis, we have the lake elevation. And on the x-axis, we have the percentage of these dust hotspots that would be covered by water at a given lake elevation. So recall that the minimum lake elevation was 4188 and a half. Right now, the lake is at 4,192.6. So all of the dust hotspots that are essentially on this plot are still exposed right now. So in order to cover up 20% of the dust hotspots, we would have to raise the elevation of the lake about 3 feet, all the way up to 4195.8. To get 50% mitigation of these dust hotspots, we have to raise the lake all the way up to almost 4,200. And to get 80% mitigation, all the way up to 4,203 and a half. And it's been a long time since the lake has been up at those levels. The Great Salt Lake Commissioner has basically established that 4,198 is kind of the minimum healthy lake for the level. But even if the lake is restored to minimum ecological health level, we'll still have dust issues. Recall that dust was the first tipping point, the first problem to emerge as the lake was shrinking, and it'll be the last to be solved if we can put water back in the lake. So we've had 2 good water years, but unfortunately, lake must be a lot higher before you can breathe easy from dust. Once again, Pat Bagley. So what do we know about the dust? Importance of soil moisture and surface crust out on Great Salt Lake. So this is work that was completed with Mark Sweeney and graduate students Thorne Merrill and Zach Clairhout. So when we start thinking about the emission controls of dust on Great Salt Lake or any other playa surface or whatnot, we've got all of these different things that can control the emissions: soil moisture, surface crust, surface roughness, vegetation, particle size distribution, mineralogy. And for this study, all we've done so far is we've taken a look at what we thought were probably two of the primary controls of dust emissions on Great Salt Lake, the first being soil moisture and the second being surface crust. So a couple of summers ago, we decided to do an artificial soil moisture test where we went out to a dust hotspot area and then artificially raised the soil moisture in the surface of the playa and basically went from the natural moisture that what was available on that day, and then ramped it up into about 2% increments in terms of soil moisture by weight. And then we used a PI-SWERL to look at the effect that that increase in soil moisture has on the emission characteristics of the playa. So in each one of those little rectangular boxes, we ran a PI-SWERL ramp test and a PI-SWERL step test to allow us to identify not only the dust flux, but the threshold friction velocity. And we also took a soil sample from the top 2 centimeters to quantify the soil moisture in that region that we were using the PI-SWERL on. And here's kind of an example of what these plots typically look like. So on the x-axis, we have the soil moisture in weight percentage. Um, and on the y-axis, we have the PM10 flux in milligrams per meter squared per second. And so here's an example where we started off with the background moisture content, which was in this case about 1.5%, had a PM10 flux of 5 on this scale. And then as you increase the soil moisture, you gradually suppress the dust emission. And we did this at lots of different sites at many different times to try and get an aggregate for how the surface behaved as soil moisture increased. Here's just another example. This one, we were taking replicates to try and get more data along the way. And they all have this same characteristic power law decrease in dust emission as you ramp up soil moisture. And we could define a minimum PM10 flux that is kind of dust suppression. And we kind of used a 1 milligram per meter squared per second as a cutoff for dust suppression. And of course, the stronger the wind, that's going to have an impact on the flux. So here, the blue dots are measurements that we took basically looking at the dust suppression, what it took to suppress the dust, the soil moisture that it took to suppress the dust versus different friction velocities. And we can do a regression on that. And we can also compare that to other work that has been done. And so using higher friction velocities out at Great Salt Lake, where we have pretty strong winds, you can see that soil moisture, soil moisture above, kind of 4% is one of those things that actually suppresses the dust at realistic threshold, realistic friction velocities of about 0.9, typically what we have for wind events out on Great Salt Lake. So our overall, takeaway from that summer was that soil moisture dominates our emission of dust at high soil moistures. It basically shuts it down. And once the soil moisture drops below some threshold, which we're saying is around 4% for Great Salt Lake, then whether or not a surface emits is largely based upon the characteristics of the surface crust. Is it intact? Is it erodible? Is there no crust? And so we can really say that out on Great Salt Lake, at high soil moistures, that dominates. At low soil moistures, it's really the surface crust that's dominating. This past summer, my graduate student Zach and I were out trying to figure out if it might be possible to regenerate crust that has broken down through artificial regeneration. And the way we did this is we set up this grid. We went out to an area that was emissive and disturbed the crust in that area. We left some of it alone for natural crust for our control. And then we treated different sections of this with fresh water from the local rivers, from brine solution from the southern arm of the Great Salt Lake, brine solution from the northern arm of the Great Salt Lake. The brine from the southern part is about 12% salinity. The brine from the northern part is about 27%. And then we used a magnesium chloride combination that was about 30% salt, just to see if we could regenerate the crust. And just preliminary results. It turns out that the eroded crust can be reset with as little as about 0.2 inches of simulated precipitation. We actually saw natural events of about that amount actually reset the crust as well while we were doing this experiment. All of the different treatments that we used reset the crust effectively, the fresh water, the natural brine, and the magnesium chloride. And once reset, the reformed crust suppressed the dust even after the soil moisture dropped below 4%. And we were only able to test for about 30 days, but all of that reformed crust uh, basically suppressed dust for 30 days. And then what happened was the monsoon came in and raised the soil moisture on our playa, and it never dropped back down to below 4% for the rest of the season. So we're going to have to do some more work to explore the limits of the longevity of that crust. And then we also are going to have to do additional experiments to figure out the longevity differences between freshwater brine and magnesium chloride applications. So looking at dust composition. So Great Salt Lake dust is primarily composed of evaporite minerals, calcium, magnesium, sulfur, strontium, chlorine, lithium, and boron, which differs from typical soil, which is your silicon, aluminum, iron, calcium, sodium, etc. Um, and we took, of course, geospatial measurements of all of the different 53 different elements and then compared those to regional screening levels established by the EPA for soil. And every single measurement that we took of arsenic exceeded the EPA regional screening levels by more than an order of magnitude. And that's a concern, obviously, because arsenic's a carcinogen that can lead to lung cancer, skin cancer, bladder cancer if people are exposed to it regularly. Um, and just to put this into perspective, if we look at the existing EPA arsenic data for PM10, there's only one site in the state that takes measurements, and it's at Bountiful, which is north of Salt Lake City. Um, the 20-year average concentration of arsenic is just a little bit below 1 nanogram per cubic meter. That doesn't sound like a lot, but in order to determine whether or not that's significant, we need to look at the hazard ratio and the cancer risk ratio. And the hazard quotient is basically looking at the exposure adjusted air concentration divided by the reference concentration. And this is for non-cancer health hazards associated with arsenic. And if we do the simple calculation of that long-term average of the arsenic concentrations divided by that reference concentration, you get a hazard quotient of only 0.06. And a hazard quotient of less than 1 indicates that non-cancer hazard really shouldn't be an issue. But if you compare instead the cancer risk associated with that, we have the once again the concentrations. We have the inhalation unit risk, which is established by in the literature of 4.3 times 10 to the minus third micrograms per cubic meter inverse. And then you use the exposure duration of 20 years for this particular data set and expected lifetime of 78 years. And you'll come up with a cancer risk ratio of just over 1 times 10 to the minus 6, which is basically 1 in a million. And that's actually high enough to pop what should be an in-depth toxicological effect analysis. None is going on, to my knowledge, but what this calls into question is, this is arsenic data that exists largely without inputs from Great Salt Lake dust. If we know that there's high concentrations of arsenic in the dust, and so if dust emerges as a significant source of PM10, it will only exacerbate an already existing arsenic problem in our city, in our area. Arsenic wasn't the only element of contaminant of potential concern. There were actually a total of 11 that were higher than the regional screening levels. Red indicates higher than the industrial exposure regional screening level, and yellow being for residents. So we have lanthanum, lithium, zirconium, cobalt, manganese, and copper. Some of these are widespread, indicating probably more natural sources. Some of these have hotspots, which are more indicative of industrial or point source. Just as an example, the really high lithium concentrations in the southern part of the lake, that's an outflow from Morton salt. They remove minerals, but they leave lithium in their effluent, and that goes out on the lake bed. Zirconium is an element that's used in ammunition. And the area on the west side of the lake is an active military training range. The area on the north that's red is a public shooting area. And the area on the right is actually an area with a lot of duck hunting in it. And then with copper, on the bottom right, the elevated copper concentrations are right next to a very large tailings pile from Kennecott Copper Corporation. The tailings pile is about 7 miles long, about 3 miles wide, and almost 300 feet high. Other elements of contaminants of potential concern: aluminum, iron, antimony, thallium, vanadium, and uranium. And I label all of these contaminants of potential concern because we don't know what the concentrations of these are in the surrounding communities, and I'll get more to that in a little bit. What do we know about the bioavailability of these metals? It doesn't matter if we have high concentrations in the dust if it's locked up in forms that can't interact with the body. So this is essentially a results from a publication that came out last year that I'm an author, co-author on, looking at the oxidative potential using synthetic lung fluid. And we were comparing the oxidative potential of the metals in Salt Lake dust compared to other regional dust sources. And compared to other regional dust sources, Severe Desert, the Tule Desert, other areas in the Intermountain West that we were comparing to, all of the most of the Great Salt Lake dust had higher bioavailability in terms of the oxidative potential. So it's not just that we have these metals in there, but they're actually more bioavailable than surrounding playas. And which communities are most likely to be impacted? Well, we know that we have these 4 dust hotspots, and prior to the passage of a cold front, we have air that moves from the south to the north, pushing dust to the north and to the east. After the passage of these cold fronts, the wind shifts primarily to the northwest, but can come from the north quadrant as well, and that pushes it in a different direction. So everybody essentially to the west of the lake and south of the lake is downwind of the lake at some point, and that comprises about 2.5 million people that are immediately downwind of the lake at some point during these events. If you just look at where that dust could be transported over time, 25-mile-an-hour winds is typically what we have associated with these dust events, and a 25-mile-an-hour wind could easily inundate many of the surrounding communities within an hour, and some of the more distant communities within 2 to 3 hours. So I did a 10-year analysis of the winds at the airport in Salt Lake, and just looking at the wind directions when the wind was actually greater than 25 miles an hour. And overwhelmingly, during that time period, when we have winds that are 25 miles an hour, the wind is from the south. And it turns out that more than 70% of all of our wind events are southerly, which would theoretically push dust to the north and to the northeast, as opposed to the winds from the northwest, which are only about a quarter of the time, which would pull it into Salt Lake County and Salt Lake City. And that's important because of the distribution about where we have our monitoring network associated with PM10 around Great Salt Lake. So since we don't have a network that actually extends much to the north or to the east of the lake, we actually have to resort to modeling. And for results on this, a paper that I'm a co-author on, it was just published in One Earth last year, looking at the communities that are most at risk from PM10 exposures from the lake and from other local sources. Here on the left, the bottom left, we have this bullseye, which is associated with exposure to pollutants from the Kennecott open pit mine, which is located adjacent there in the Ochre Mountains. But the red concentrations are the ones that further north are the ones that are associated with emissions from the lake bed itself. And the communities that are most likely to be impacted are, immediately to the northeast and south of the lake, obviously right around the periphery. But that extends quite far north, away from Farmington Bay and the lake. And that's also an area where we don't have monitors. So I've kind of talked about what we do know about Great Salt Lake, but what don't we know about Great Salt Lake and why? We really have a very poor handle on the frequency of the dust events. We don't know, for the most part, the PM10 concentrations in the most vulnerable communities, the ones nearest to the lake. We don't know the concentrations of the metals that are transported to these vulnerable communities. And we really don't know the answer to whether or not the dust concentrations violate the national ambient air quality standards in these vulnerable communities either. And so ultimately, I'm left with being unable to answer the question about whether or not Great Salt Lake actually poses a health hazard. It's not for my suspicions, but it has to do with a lack of a coordinated dust monitoring network in northern Utah. So what do we need to do? Well, we need to have better measurements to calculate the dose of exposure for dust to the people who live in these communities. And to do that, we need concentration measurements, frequency measurements, and bioavailability measurements. For the concentration and frequency, we really need to augment our PM10 monitoring network from the Division of Air Quality. And for bioavailability, we've started down that path, but we still require additional research in order to quantify the bioavailability of all the different potential contaminants of concern. So let's take a look at the current state of PM10 monitoring at Great Salt Lake versus Salton Sea and Owens Lake. So what we have here is we have the lakes drawn to scale. Owens Lake, of course, being just more than 100 square miles, and it has a total of 9 monitors, 8 of which are on the periphery of the lake, one in the adjacent community. If we look at Salton Sea, which is an emerging dust source of concern, California, and just in the last 2 years, has put in 14 monitors around Salton Sea, with at least 6 of those being on the lake shore and 8 of those being in surrounding communities. And contrast that with what we have at Great Salt Lake, where prior to September of last year, we had 4 monitors, none of which was located within 15 miles of the lake. None were on the shore of the lake or in the vulnerable communities. The state just did add the 2 monitors in red starting in September. Those are better, but still are more than 7 miles away from the lake bed. And just to put this into perspective about the relative populations in each one of these areas, the Owens Lake Valley essentially has about 25,000 people. Salton Sea is about 250,000 and Great Salt Lake is 2.5 million. Yet the monitors that we have are insufficient in order to be able to answer very basic questions that we need to answer about the impact or potential impacts of Great Salt Lake dust. And so back to Bagley. Guys, let's go to the scariest, most terrifying attraction in Utah, Great Salt Lake. And I know that the New York Times has labeled our dust as toxic dust, and that has gotten a lot of press. What scares me more is just the fact that we don't have data to determine whether or not it's an actual health hazard. And unless we change that rapidly, 5 years from now, we're not going to have any more answers at all. Now, luckily, this message has been moved up through this legislature and to the governor, and the governor has a budget request for $651,000 of ongoing funding to try and augment and increase our dust monitoring in Utah. And we'll see if that actually gets passed through the legislature. And the one thing I didn't mention is that the Division of Air Quality, although we had very few monitors in Great Salt Lake, in part because they had actually been shutting down PM10 monitors. Because they didn't want to deal with filter-based monitors, and they replaced some of those with a real-time instrument that wasn't a TEOM. And unfortunately, the instrument that they chose has been failing during dust events. So it's to add insult to injury, the filter-based monitors went away. They replaced them with real-time monitors that were ineffective at measuring and quantifying our existing dust events. So it's not just an issue of funding, it's actually picking the right instrumentation to go along with that as well. And with that, I just want to acknowledge my funding sources and collaborators. And I'll open it up for questions.
Thanks, Kevin. This is a fantastic talk. We have some time for questions. Is there Anybody? I didn't see anything in the chat. So if you have a question, feel free to just unmute yourself.
Kevin, I got a question. This is Randy Martin.
Yep.
Um, Fascinating talk. Great. I always love your work. Um, as far as your hotspot areas, was there anything that was kind of in common to those areas that we could use as a predictive measure to see where hotspots might start appearing in the future?
Yeah. So the things that they had in common were they had the particle size distribution was smaller in those areas. There was more silt and clay. So that is to be expected in Farmington Bay and Bear River Bay because we have the Bear River, the Jordan River, Weber River coming into those areas, delivering that silt and clay. So that's one of the things. The other thing is that we've also got maps of the crust distribution on Great Salt Lake as well. And so it really comes down to places that have no crust, shallow eroding crust, and saltators. So there are certain parts on the lake where we have significant amounts of sand that move around that can act as ablaters and can actually destroy fragile crust along the way. And so what we do know is that the threshold friction velocity varies among the different parts of the lake bed. Farmington Bay has the lowest threshold friction velocity for emission, which means that it's the easiest one to actually generate the dust, and that's the one that actually is closest to the largest population. Bear River Bay has a much higher friction velocity, so it takes a stronger wind in order to generate dust in Bear River Bay.
Questions are
Thanks.
coming in now.
Mhm.
Bill Spriggs wondering if is there anything about deposition on snow that warrants measurement or testing?
Yeah, so
For
there
example, snow melt.
it's a really big deal here in Utah. And Dr. Mackenzie Skiles at the University of Utah in the Department of Geography is the expert on that here. She's been taking dust on snow measurements for more than a decade. And her modeling work has indicated that in an average year, the dust on snow leads to an accelerated snow melt of 2 to 3 weeks in the Wasatch Mountains. And that has huge implications on the hydrology of the area in terms of potential water storage, water capture. And just an example, 2 years ago, we had a record snowfall. We actually had 200% of normal snowpack. We had twice the amount of snow water equivalent in our mountains. And everybody was thinking that it'll take until July or August for that snow to melt. And it was gone by June 1 because of late season dust events that accelerated the snow melt.
Another question. The arsenic appears to be all around the lake bed, suggesting it's natural. Do geologists or geochemists have insights on its ultimate source? And are there anthropogenic sources of arsenic acting as magnifying hotspots for arsenic in the dust?
So the answer to that is yes and yes. So the arsenic in the lake bed is not anything that was unexpected. Most of the playas in the western U.S. have higher concentrations of arsenic, including Owens Lake in California. Interestingly, the arsenic concentrations at Great Salt Lake actually are higher than those of Owens Lake. And that could be a combination of anthropogenic industrial inputs as well. We have lots of legacy mining activity with that could contribute to that as well. But we didn't see on the lake bed itself, hotspots associated with an individual industry. It's probably more legacy mining that has impacted that in addition to naturally occurring arsenic.
Do you have any idea how much dust coming from Salt Lake contributes to the cold air pool related pollution in the Salt Lake area?
I typically think of those as two separate things. So when we have cold air pools, we typically have really weak winds or no wind at all. And so it's not typically the season when we expect to have dust. So we have in Utah, we have our wintertime cold air pool pollution, which is primarily local pollution that's trapped. In the summertime, we have elevated ozone, local and transported, along with wildfire smoke. Generally speaking, we have good air quality in the spring and the fall. But that's the time period when the dust is most likely to occur. And if the dust events become more frequent or severe, then we are in danger of moving from a time period where we have seasonal air quality challenges to year-round air quality challenges.
What are the most likely funding sources for additional air monitors, and is that gaining any momentum?
Yeah, so the state is the primary place we're looking for the monitoring. And as I mentioned, the governor put a specific budget line item request of $651,000 of ongoing funding to specifically for PM10 dust. And that is intended to be a network around Great Salt Lake, but in order to sell it to the rural legislators and the legislators in the southern part of the state, they were also justifying it in terms of the emerging issues with valley fever in the southwestern part of the state.
We have one hand up. Scott, do you want to ask your question?
Hi. Yeah, super interesting talk, Kevin. So when you look at arsenic risk factors, so it looks like maybe you were just looking at inhalation. Is that
Yeah.
correct? Okay. Yeah. So we find that if we also do multi-pathway risk factors, they're much, much higher.
Uh,
And
just including the hazard risk or just the cancer risk or both?
both actually.
Both,
So the
okay.
hazard index of 1 nanogram is approximately 6.
Really?
Yeah.
Okay.
And then cancer is roughly 80 or 90 cancers per
Wow.
million. We
Okay.
find that we find that all around our region as well.
Mhm.
Level is a bit lower than that, but kind of it's pretty typical around the rest of the US. So we think that a lot of it is actually naturally occurring.
Yeah, this is not an area that I'm really good at, so I'd love to talk to you offline to find out more about how you've approached that.
Sure. Yeah, that'd be great. And we've done a whole analysis of all the US data as well, if you want to.
Okay.
It'd be great.
Mhm.
Another comment from Madeline Kelly. Great presentation. Several of us are here watching this together at USGS in Flagstaff, Arizona. We are curious why the relationship between water surface elevation and hotspot area was so linear. Is that due to the very flat topography of the lake bed, or possibly did we misunderstand the figure?
Nope, it's not something that I expected at all. It just is a vagary of a peculiarity of the topography of the lake bed, such that the surface area and the hotspots are linearly related. I hadn't expected that, but it's an R squared of like 0.99 for each part of the lake separately and the lake as a whole. So it's really just kind of amazing. But the beauty of this is from a policy standpoint, you can look at this and you can do the slope of the line and you can say for every foot of increase of the water level above 4194, you can decrease the number of hotspots or the hotspots by about 7% per foot. But one of the things that I'm having trouble messaging, of course, is that Great Salt Lake is a terminal basin lake that waxes and wanes. It has a long-term natural elevation of about 4,200 feet. So if that's the long-term natural elevation of the lake, all of the hotspots that I've identified above 4,200 feet could theoretically be considered natural dust sources, and the ones below 4,200 feet could be considered the ones that are the result of human intervention. That's one way to look at it. I haven't really talked about that publicly because it's a nuance that's hard to explain, but to this group, I think everybody would kind of understand that.
We have a couple questions about whether chemistry of the dust and snow has been measured, and is it the same as what's on the playa, and has there been any toxicity measurements of that?
Yeah, so Mackenzie Skiles and Greg Carling at Brigham Young University have both taken significant samples of dust and snow and done chemical composition on that. And then we work with Derek Malia at the University of Utah to do modeling of back trajectories to figure out where the footprints of that comes from. And both Mackenzie Skiles and Greg Carling have done source apportionment for the dust in the Wasatch snowpack. And they determined in a publication a few years back that 90% of the dust that was depositing in the snowpack was from regional playa sources. Not necessarily Great Salt Lake, but regional playa sources, and 10% was kind of urban dust. And then, we can look at individual years, and on any given individual year, the contribution of Great Salt Lake dust to the Wasatch Mountain snowpack is on the order of a quarter to a third of the dust that's being transported. I often say that, Great Salt Lake is not a very prodigious dust source relative to other dust sources in the region, but the proximity to the population makes it the one that is of most concern. We have other dust sources in Utah that produce a lot more tonnage of material, but they're at least 100 miles away from the population centers, and so their impact is a little bit muted because of that distance. But we see that impact in the snowpack. And in terms of the bioavailability of the material in the snowpack, Greg Carling was part of a study where they were looking at they did sequential leaching of the metals, and they were seeing significant bioavailability in the sequential leaching from the dust that was connected in the snow as well.
We have a comment here about terrace. Kumar, excellent talk and thank you. I was intrigued by the 4% soil moisture being more or less a threshold above which dust suppression may begin in earnest. I thought of an analog with regard to fires here in Southern California, in which fuel moisture is usually very low, less around 4 to 6% when fires can start and spread rapidly. Might there be a continuum of this threshold in terms of fire and dust of sorts?
Yeah, I think so. In terms of the fuel moisture, you've obviously got the fuel loading, the fuel moisture, all contributing there. For the Great Salt Lake, I mean, we've got this different soil moistures, and of course, it depends upon the wind speed as well. Stronger the wind speed, the higher the moisture can be, and still produce dust. For example, this last dust event that we had in January the 21st, when I went out and was measuring soil moisture from areas that were blowing. The lowest soil moisture that I found was like 5.5%, but the winds were pretty strong.
Time for a couple more comments. One from Joy Bell. Thanks, Kevin. Great talk. I was curious from a modeling perspective, would you recommend constraining emission models to the hotspots you discovered? Or do you think that the conditions for a hotspot are sensitive enough to changing climate and weather that the whole dry GSL should be considered as a potential emission source of dust?
So what I've learned from going out to the playa repeatedly is that every winter our soil crust resets. And it's really the meteorology that happens during that year and the coupling between the evapotranspiration and the groundwater that controls how quickly that surface dries out and where that surface dries out. Because of the key tie between the surface moisture and the groundwater, and that's tied to subsurface features, the hotspots tend to recur in similar areas from year to year. And so I think that I originally had this kind of linear notion in my head that year after year, the size of the dust hotspots would continually grow and grow and grow. And I don't necessarily think that's the case because of the resetting of the crust and the ties to the subsurface geology that allow certain areas to dry out. So I think that over time, I'm not expecting huge differences in soil moisture of crust, but I could be wrong in terms of the evolution of the crust year over year. So that's just kind of my hypothesis of what's going on right now.
One last question. Do you have any idea about dust event forecasting accuracies in this area by weather forecasting agencies like the National Weather Service?
It doesn't exist. The National Weather Service, all they do is when there's a high wind event, they will make an announcement that there could be blowing dust. Even when we're in an active dust event, they're not really talking about that, and they don't really have the capability to forecast that right now in the local forecast office. So that's something that Derek Malia at the University of Utah has been trying to get funded for a while now, an operational kind of dust forecasting for this region. And through NSF grants and other sorts of things, we've been gradually improving the model. It's not operational yet for purposes of warning the public sort of thing, but that's kind of where the science needs to go. So that people can be warned about this and be educated on what they can do to protect themselves.
Thank you. I think that's the time we have for questions. It looks like we've got to everyone. So Kevin, thank you again for this presentation, and thank you everyone for your great questions and discussion.